Welcome to Higher Structure Seminar Series. Today our speaker is Keremcan Doğan from Gebze Technical University and he will tell us about proto bialgebroids for exceptional geometries. We thank Keremcan and please, yeah.
Okay. Hello everyone. Thank you İlhan Hocam for inviting me to give this seminar. Let me start and I will talk about some algebraic structures related to some physically motivated geometries. Let me give my overview. I will first try to motivate you to uh, understand why we are trying to define such generalizations of already existing Lie bialgebroids, and this motivation will continue with T duality. It's again kind of motivational for this talk, but it's also in our future plans. And I will talk about bialgebroids, which is a term that we introduced, sort of, and then I will extend this bialgebroids to proto-bialgebroids by introducing some twists. Then we will come back to some physically motivated geometries, and these exceptional geometries will will be the topic, and we will discuss some higher Kur'an algebroids, some non-Poisson structures, and we will relate the third and fourth topics to these geometries. And then I will conclude with some possible future research directions. Let me start with my motivation. Currently, our most successful physical theories are general relativity and quantum field theory. General relativity explains gravitational stuff in the universe, and the other three forces and all the other parts, other types of interactions in our universe is explained by standard model, and which is sort of like a quantum field theory, but both some experimental and some mostly theoretical uh, ideas force us to combine these two theories in some way to get something called a quantum gravity theory. But currently, we don't know how to express such a theory, but we have some candidates for such a job, but we don't know which one is the correct one, or maybe all of them are wrong, but we have some ideas how to express quantum gravity, and my physical motivations comes from string theory and M theory, which are probably the strongest candidate for this type of quantum gravity theories. But for this kind of theories, we need to change our geometry, sort of. We in string theory, for example, we have higher dimensional spacetimes like 11 dimension, 10 dimensions, 26 dimensions, but we need to sort of uh, compactify our space-time uh, to get the four-dimensional space-time that we daily experience. These extra dimensions should sort of uh, curl into each other, into itself, and they should be sort of compact. But this compactification process in our theory creates some surprising results, and some of them are listed here. For example, we get some unusual fields with weird gauge transformations. Our Lagrangians are actions that uh, give the information about the equations of motion. They are quite complicated in such theories. And there are something called fluxes. We will not explain them, but we will slightly touch on them. There are geometric and non-geometric fluxes and these are quite important for string phenomenology. And more importantly for us, the notion of symmetry in point particle theories should be extended to some higher, not higher, but some generalized sense. These symmetries should be extended to something called dualities, which are absent in particle physics. And these dualities will be sort of our main motivation. Let me give you an example of this weirdness. Uh, as I told you, gauge transformations in string theories can be uh, weird than we expect from particle physics. For example, uh, most of the string actions that we deal uh, have some mutual fields, and these fields are metric field G and a two-form field called Kabramov field B. And the gauge transformations of the metric are generated by some vector fields, but the gauge transformations of this two-form field are generated by one forms. And in general, we have such gauge transformations. And if we sort of combine two gauge transformation together in order to get another gauge transformation, usually in gauge theories, we have only vectors, and vector fields satisfy a Lie algebra. So this algebra of gauge transformation sort of close. But for combination of the gauge transformation of metric field and Kalbramon field, if we combine two such gauge transformation, then we get a gauge transformation expressed in such terms. And today we call this combination of terms as Coulomb bracket, which will be important for our discussion later. This is unexpected for particle theories, but this kind of weird gauge transformation always exists in string theory. The other weirdness is T-duality, which is a symmetry of not only one theory, it also connects different theories, different solutions of different theories may be mapped under this T-duality. Let's start with some basic example of this T-duality. If we consider a compactification where the extra dimension is only one circle with radius r, particles can only travel in this extra dimensions, but since we have extended objects like strings, strings can do more. They can also travel around the extra dimensions, but they can also, if they are closed, they can wrap up the compact dimension circle. And if we count the uh, number of wraps, we get some integer, and we will call them a winding number, k. And as circle is compact, from quantum mechanics, we know that the momentum should be quantized. So we get some momentum number, which is also an integer. And if we express the energy of the string, then we get this quantity E. And you can see the winding number and the momentum number. But if you change your winding number with momentum number and your radius with 1 over radius, you can see that the energy doesn't change. And this is like the most basic T-duality example. We will see other types of T-dualities. For example, in terms of this G and B field, the T-duality can be expressed by something called Bouchard rules, where this is all the T-duality is first discovered. So uh, for such for such a construction, we should have some isometries in our uh, isometries for our metric. And when we have isometries, by using the killing vectors, we change the entries of the metric and entries of the Kaldramon B field according to these rules, these Bouchard rules. We get another solution of the supergravity equation. We start with some G and B, which solves the supergravity equations, and we do this weird transformation, sort of mixing the components of G and B together. When we apply this T duality by Bouchard rules, we get another solution. For example, this is a simple one. We have the usual Euclidean metric, and we have some B field, two-form field like this. And if we apply this procedure in the direction Z, then we get another metric, and B field is vanishing. And this is also a solution of some supergravity equation. This is the abelian T duality, and this procedure gives us a way to combine the components of G and B in a non-trivial way, but still we get some solution. And double field theory is based on the idea that this T duality should be elevated to a usual symmetry, let me say, and it's formulated as a GR-like theory, and they transform the idea of diffeomorphism, which are generated by GLD in general relativity, but in double field theory, we get some symmetry group ODD, and this symmetry group arises because we do some compactification of some supergravity theory. And when we compactify, we always have some residual symmetry in the lower dimensional field theory. And if we compactify a d-dimensional torus, we get from the type 2 supergravity equations, we get the double field theory. Yeah, we get the ODD group, and the DFT framework uh, sort of formalizes this ODD symmetry in a non-trivial way. And in order to express T duality in this double field theory framework, we need something called a generalized metric, which combines again the components of G and B in a non-trivial way. And this generalized metric is a tensor on the generalized tangent bundle. And this generalized tangent bundle, without even any physical motivations, are this generalized bundle is studied thoroughly in the mathematics literature. And we will see that this is actually a Courant algebroid, which we will define now. We had the Courant bracket of a vector field plus a one form, and the Courant bracket makes the generalized tangent bundle, tangent artı cotangent bundle, tangent plus cotangent bundle, Courant algebroid. And these are the main objects that we are interested in actually. We will be interested in a generalization of Courant algebroids, and actually the whole literature of algebroids are actually almost always an extension of a Courant algebroid. Let me define it. It's a vector bundle with some extra structure. As all algebroids, we have a map called the anchor. It is a vector bundle morphism from the vector bundle that we are interested in to the tangent bundle of the base manifold. And we have a product, we have a bracket on the sections of this vector bundle. I write E, but this should be seen as the sections of E. I didn't want to put everywhere gammas. And we have some metric. Usually a metric eats vector fields, but we just have some arbitrary vector bundle. And this metric eats the sections of the vector bundle and gives us a smooth function. This is the structures in the Kur'an algebroid, and these structures should satisfy some conditions. And the first one is the Jacobi identity, like the usual Lie algebra. This is just a Jacobi identity. In order to have a Kur'an algebroid, oops, the symmetric part of the bracket should be given in a specific form. This is not really important for us at the moment, but just some metric in the definition and its exterior derivative. And as this is a one form, in order to map to E again, we use the matrix inverse. And we also have metric invariance. These three properties are the defining properties of a Kur'an algebroid. If we have a metric, if we have a bracket, and if they satisfy all these three properties, then we call the structure as a Kur'an algebroid. And these Kur'an algebroids are actually were first appeared as the Drinfeld table of Lie bialgebroids in the literature. So let's first define a Lie bialgebra. We have a Lie algebra G, and its dual G star is also a Lie algebra, and there is a compatibility condition between these two Lie algebra structures. Under this compatibility condition, we have a unique Lie algebra structure on the direct sum of the G and G star, such that these two properties are satisfied. The canonical pairing should be invariant, and both G and G star should be some subalgebras which are isotropic. And this unique Lie algebra structure is called the Drinfeld double of the Lie bialgebra. And if we elevate these constructions to algebroid level, instead of a Lie algebra, if we start with a Lie algebroid, I didn't define it, but it's a vector bundle, and its product satisfies the same conditions as the usual Lie bracket of vector fields. So it satisfies the Jacobi identity, it is antisymmetric, and it satisfies the Leibniz rule when we put some function next to the vector field. If we do this replacement with a Lie algebroid, and if we require the same conditions, then it is proven that on the Drinfeld double A plus A star, now instead of a Lie algebroid, we get a Kur'an algebroid. This is a quite important difference. If we add G and G star, and if we require some conditions, then their Drinfeld double, their direct sum is again a Lie algebra. But if we start with some Lie algebroid, then the Drinfeld double A plus A star is a Kur'an algebroid. It's not a Lie algebroid anymore. And for this Lie bialgebroids, the compatibility condition is given like this. We have a Lie type bracket on the vector bundle A, and by using this Lie bracket, like we did in the usual geometry, we start with some Lie bracket of vector fields. By using that Lie bracket, we can define Lie derivative and exterior derivative. Now we start with a Lie algebroid bracket on A, but we can still define a Lie derivative and exterior derivative in a completely analogous way. And this L in the right hand side is the Lie derivative corresponding to the Lie derivative constructed from the bracket on A, but D star is constructed from the bracket of A star, because A star is also a Lie algebroid. By using that bracket, we can define a new exterior derivative or Lie derivative, and we can denote them by some star. So this is the exterior derivative constructed from the bracket on A star. And this is the compatibility condition defining Lie bialgebroids. If the Lie algebra structure on A and A star satisfy this compatibility condition, then A plus A star is a Courant algebroid as proven in these articles. And T duality can be also expressed as a transformation in the framework of Lie bialgebroids. If two uh, two different vector fields have the same Drinfeld algebra, vector bundles, Lie algebroids, have the same Drinfeld algebra, they have the same uh, direct sum, but they are distinct. It is proven that T duality can be expressed as a transformation changing A to A hat. So the different decompositions, different Manin triples of the same Drinfeld double correspond to T-dual solutions. Of course, this is a huge sentence with sort of background, but this is the biggest T-duality, the most general T-duality in town at the moment, and it can be expressed in the language of Lie bialgebroids and their Drinfeld doubles. This is basically the uh, first motivation for us to express generalizations of Lie bialgebroids, which are called bialgebroids in our own literature. Uh, as I told you, there are some extension of symmetry notion called dualities, and this was the T duality. But there is also S and U dualities in string theory. And we will be interested in bialgebroid structures which can be related to U duality. And these dualities, as I mentioned, they connect different types of string theories and their solutions together. And U duality is sort of like a combination of this T and S duality. We will try to explore the relation between T duality and bialgebroids, and this U duality is an extension, is a generalization of T duality. So we want to find the correct generalizations of Lie bialgebroids so that this new extended bialgebroids might be useful for U duality, which is itself a generalization of T duality. So this is our main aim. And this motivation comes from something called exceptional field theory, like double field theory, where the geometric setup is expressed as the tangent bundle and cotangent bundle. These are basically some extensions of that idea. If we again compactify now the 11-dimensional supergravity on a d-dimensional torus, then effective lower dimensional field theory has a symmetry group, the exceptional groups. And these exceptional groups in the lower dimensional field theory can be uh, realized as a symmetry if one introduce some extension of the underlying geometric setup again. And these new setups are useful for U duality formulations. And there are many different vector bundles appear in such compactifications. Uh, and you can see some examples here. For example, these two forms, two forms plus five forms, or one form valued seven forms. These are the vector bundles that these physicists try to construct some geometry. These are physically important vector bundles which are useful for physics. But Tm plus T star m was sort of unique because the tangent bundle and cotangent bundle, they are just duals of each other. So they have lots of extra structure that connects the two of the vector bundles. But as you can see in these examples, the relevant vector bundles are quite arbitrary. So our uh, aim is to realize this arbitrariness and try to construct everything not by using some specific examples and some specific forms, but let's consider a vector bundle consisting of two different parts, A and Z. They are not dual in the usual sense. They are not dual vector bundles, but again, there is still some, in some sense, they are dual because the physical geometry and the U duality requires such notions of dualness. And so we will be interested in some vector bundle E, which will be decomposed as A plus some Z. And these two vector bundles will not be dual in the usual sense. They can be of different rank, and most importantly, they do not come with some canonical Lie algebroid structure, because the tangent bundle is always a Lie algebroid because there is a canonical Lie algebroid structure coming from the usual Lie bracket, and cotangent bundle, uh, if there is a Poisson structure, then it's also a Lie algebroid. But for weird vector bundles, they do not have any canonical Lie algebroid structure, and usually they are not Lie algebroids. Some other algebroid structure. So again, we want to be as general as possible. So we will define an algebroid without any extra assumptions. It will be just a triplet of objects. Again, we have a vector bundle. We have a vector bundle morphism to the tangent bundle. And again, we have a product. An algebroid will mean just this. But of course, in order to relate some existing algebroids, we will have lots of algebroid axioms. And this is just a list of algebroid axioms that are frequently used in the literature. For example, right Leibniz rule, left Leibniz rule, Jacobi identity, like some of these are already in the definition of the Kuran algebroid or Lie algebroid, but these are rather general forms of axioms that an algebroid can satisfy. For example, for Kuran algebroids, the symmetric part was in a specific form, but we can study just a metric, and this metric doesn't have to have some uh, function, smooth function as an output. It can be taking values in some arbitrary vector bundle. And here we can have some arbitrary first order differential operator, or again, metric invariance can mean something else with some new differential operator. These are rather general forms of algebraic axioms because we want to make everything as general as possible so that physically motivated vector bundles can fit when necessary. Okay? For T duality, Lie bialgebroids are uh, uh, enough, but we don't know which type of algebroid structure will appear in U duality. Of course, we have some ideas, but in order to have a general as possible framework, we study algebraic axioms separately and without focusing on a specific algebraic. So these are the algebraic axioms that we are interested in, but I will give only examples from the Jacobi identity. Again, we will be interested in a vector bundle E, which is equal to A plus Z. And if we require both A and Z to be subalgebraids of this direct sum, then the general form of the bracket would be something like this. The a bracket on A, here you should read it. This is a map from A times A to A. This is Z times Z to Z. So this is the A part. This is the Z part. And for example, L takes some vector field and one form, it gives another one form. This is the general form of such a bracket. And currently, L, D, iota or L tilde, these are just some notation. They don't mean anything currently, but we will try to give some meaning to them by using these algebraic axioms. Uh, by uh, doing a similar construction to Lie bialgebroids, we take this bracket and we ask the question when the full bracket satisfies some condition, the satisfies some algebraic axiom that we list. What are the conditions for the decomposed objects? Like what is the condition of L, D, L tilde to get the desired algebraic axiom for the full bracket. These are called compatibility conditions. They are also quite important for physics. And we analyze each algebraic axiom separately. We sort of find the necessary conditions so that the full bracket satisfies Jacobi identity, for example, or left Leibniz rule. We ask for every algebraic axiom separately and derive the compatibility conditions on these objects separately. And this was done in our paper with Aybike Hoca and Cem Yetişmişoğlu. We derived here all the compatibility conditions that are needed for the algebraic axioms that we list. And as we discuss each algebraic axiom separately, we use the term bialgebroid without any adjectives because we have Lie bialgebroids and they satisfy such and such axiom, Jacobi identity and antisymmetry, for example. But we now have the full, not full, but a long list of axioms, and we do not focus on one adjective. Any subset of these axioms will correspond to some different algebroid. Choose 1, 2, 3 axiom, you get some Kur'an algebroid. Choose another ones, you get some, I don't know, Atiyah algebroid, just some algebroid with some random name. There are many algebroids in the literature, so use we don't use any adjectives, and we call when A and Z satisfy the necessary compatibility conditions, we call the pair A and Z as bialgebroids. And as the Drinfeld double of Lie bialgebroids gives us a Coulomb algebroid, we find the Drinfeld double with the relevant properties. The compatibility conditions will give you the desired properties on the Drinfeld double. And this study extends Lie bialgebroids in a more general setup, and it's also directly related to matched pairs of algebroids, which is also an important notion in the algebroid literature, which is one of the main motivations for our previous work. Now let me define a calculus. As I told you, we will try to give some meaning to these arbitrary objects, and the letters are not chosen randomly. These will be some generalization of Lie derivative, exterior derivative, and interior product. So they will be giving a generalization of Cartan calculus. So that's why we name this as calculus. Uh, we have some vector bundles, again A and Z, and we also have another curly Z, which is the image of this iota map. If we have three maps with these domains and ranges, again our uh, analysis is this. We evaluate left Leibniz rule, right Leibniz rule, Jacobi identity, and if they do not mix L and L tilde or D and D tilde maps together, we separate these compatibility conditions, not compatibility, we separate these conditions and we require this L, iota, and D to satisfy these conditions that do not mix with the tilde ones together. These are the necessary conditions for such a construction. These are some just C infinity linearity properties of the uh, maps L, iota, and D, and these are the other conditions which are actually required for the Jacobi identity. And if we require these six properties, then we call these objects as a calculus. And you can actually later prove that the Lie derivative and interior product and exterior derivative actually satisfies all of these properties. For example, this is exactly the same. This is just the Jacobi identity of the Lie bracket, sort of, acting on one forms. Uh, for example, here, if you uh, commute L and D, then this is just the commutator of iota and Lie derivative, which holds for the usual Lie derivative, of course. But for our maps, we cannot commute L and D. This is not possible. The ranges and images are not compatible. But we can show that actually these weird properties are indeed satisfied by the usual Cartan calculus. So in a sense, we extend the Cartan calculus, which is which can be seen as a calculus on T star M induced by the tangent bundle. And this is why in the Lie bialgebroid cases, there is a notion of Lie derivative, interior product, and exterior derivative, but for arbitrary A and Z, these notions do not exist. So we define this notion, which exists for arbitrary vector bundles, and when we focus on the tangent and cotangent, we get the usual same stuff. Let me show you the compatibility conditions for Jacobi identity. These compatibility conditions will mix the tilde elements with untilde elements. So these are not that crucial, but these are the Jacobi identity compatibility conditions. And we also have their duals. So like L tilde A bracket, this change everything with tilde and you will get their duals, sort of. So we have six different compatibility conditions to have the full bracket, to have the Jacobi identity. We have six conditions, but let us recall Lie bialgebroids. They have only one compatibility condition and they are done. But now we have six, but we can show that five of these conditions, when we consider A and Z as A and A star and put them some Lie algebroid structures, we see that five of our conditions are automatically satisfied. We only have one, which is this one actually, and we can prove that this one actually transforms to the usual compatibility condition when A and Z are both Lie algebraics. This condition becomes this. So we can say that we actually extended the Lie bialgebroid construction to a new, more general bialgebroid construction. Now let's come to proto-bialgebroids. Now we will remove the condition for A and Z to be subalgebroids anymore. So we will allow some twists, H and R maps. Here you can see that, for example, let's focus on HUV. In the full bracket, now we have a HUV term, which is on the Z part. So there is a map which eats two elements from A and gives us an element from Z. So A now under this product is not a subalgebroid. So it sort of goes out to Z. And also we have the R twist. So Z is also is not a subalgebroid anymore. And we basically do a similar analysis when these two twists exist. These two twists are actually also important from a physical point of view because when there is no R and H, if we take a basis and express the structure functions like this, when there is no R and H, we don't have this term H, A, B, C, E, C and R, A, B, C, E, C. But when we express these terms, we get the full commutational relations. This is mathematically a, a trivial statement, but physically these structure functions are actually corresponding to these geometric and non-geometric fluxes, which are extremely important in string theory. These structure functions and their existence are quite important for string theory and also they are crucial for sigma model business. So these types of brackets will include all types of fluxes that are useful for string theory phenomenology, and the T-duality can be also seen as a transformation between these structure functions. So we will now extend the notion of bialgebroids in the presence of twist, and again we have the same set of axioms. We repeat the process and find the compatibility conditions again. For example, the conditions in the calculus definition was all of these left-hand sides were zero, but in the presence of H twists, now we have some complicated terms. And also the compatibility conditions, for example, for the Jacobi identity, gets also some contribution from the H twist. But for example, this one doesn't get transformed. By repeating this process, we actually arrive at another generalization called proto-bialgebroids. Because in the literature, there is a notion called proto-Lie bialgebroids. These are extensions of Lie bialgebroids. And when we introduce this H and R twist, we do the same generalization. From bialgebroids, we go to proto-bialgebroids. As in the literature, proto-Lie bialgebroids are generalizations of Lie bialgebroids. Uh, the important point of this proto-Lie bialgebroids, they still have something called something uh, related to their Drinfeld doubles, and their Drinfeld doubles, so A plus A star, is still a Courant algebroid. They are not Lie bialgebroids anymore. They satisfy different conditions, and still their direct sum is still a Courant algebroid. And the first notion of these proto-Lie bialgebroids are actually defined in the language of supermanifolds, but there is also a bosonic definition in the paper here. Let me not read the name. Uh, we, we by performing a similar analysis, we actually arrived at generalization of this proto-bialgebroid notion too. We again uh, use all the compatibility conditions. When we take A and Z instead of uh, A and A star, we get again more compatibility conditions. But when we consider Z equals to A star case, some of the extra conditions are trivially satisfied again, but the remaining ones are actually the defining property of the proto-Lie bialgebroid. So we can say that we generalize the notion of proto-Lie bialgebroids to proto-bialgebroids. Let me. Now, this is a concrete example. This section will include some concrete example which is useful for exceptional geometries. Let me remind you the vector bundles that are physically important. These are the important vector bundles, and because of this reason, we will focus on the tangent bundle direct sum P forms as an example. Okay. And as you can see, this should be also T star. The first one is two forms. And when P is equal to 2, we get this case uh, completely. But the other things also have some higher degree P forms. So we will be interested in tangent bundle plus some P form. And we want to construct a full bracket on this vector bundle with everything that we considered here. We can use some results from the literature. First of all, there is something called a higher Kur'an algebroid. It is defined in the same vector bundle and it is defined with this bracket. As you can see, we can use this bracket, which is consisting of the usual Lie bracket of vector fields and usual Lie derivative and usual exterior derivative. We can use these four terms for this term and these last three. That's okay. But we have still the tilde versions. But in the same article, we can also find a bracket on P forms. But now this is constructed by using a Nambu-Poisson structure. It is basically a P plus 1 vector field, pi, satisfying some condition. Under the when this structure, Nambu-Poisson structure exists, we can define a product on P forms. This is a map eating two P forms and it gives another P form. And it satisfies the Jacobi identity, for example. It has some symmetric part though. It's not a Lie algebroid. So it's a Leibniz algebroid. And the bracket is called the causal bracket. And if we take this bracket, we can find a bracket on Z. Okay, but we still need to construct L tilde, D tilde, and iota tilde. And these are not existing objects in the literature or in this specific paper. But in order to construct them, we first come back to A star business or TMT star M business. And let's focus on triangular Lie bialgebroids. These are special case of Lie bialgebroids. Now we are interested in tangent bundle and the cotangent bundle. If we have a Poisson structure, then by using the causal bracket, the same bracket as before, Now we have a Poisson structure instead of a Nambu-Poisson structure. So it's a bivector. Now we can show that this is actually a Lie bracket. So it is antisymmetric. Jacobi identity holds, and also the right-Leibniz rule is correct. So this is a Lie algebroid structure on the cotangent bundle. But there is also an important property. This cotangent bundle Lie algebroid induced by the Poisson structure is automatically compatible with the usual Lie algebroid structure on the tangent bundle. So when we have a Poisson structure and when we construct a Lie algebroid structure on the cotangent bundle by using this Poisson bivector, then we automatically get a Lie bialgebroid. And such Lie bialgebroids are called triangular. And as the cotangent bundle is also a Lie algebroid, we can construct L tilde, D tilde by using this bracket. As I told you, the usual exterior derivative and Lie derivative are constructed from the usual Lie bracket. Now we get another Lie algebroid structure, but T star M and Tm, as they are dual, starting from this bracket, we can induce some L star, L tilde, D tilde maps, and these are actually already existing in the literature, and they are called Poisson calculus. So they are Lie derivatives, but they take the Lie derivative of a vector field with respect to a one form. And actually, this Poisson calculus is also a calculus in the sense that we have introduced. Now, but we cannot use the usual triangular Lie bialgebroids and extend it for Nambu-Poisson structures because P forms are not duals of the tangent bundle. So we cannot elevate this causal bracket for a P form, and we cannot generate a Lie derivative acting on vector fields when the degree P is greater than 1. When P is 1, this construction works, but for higher P's, this doesn't work, so we cannot directly get to Poisson calculus. But in our work, we actually show that a physics result due to Halmagyi is actually equivalent to a triangular Lie bialgebroid construction. He is doing some stuff for uh, physics purposes, but he's trying to uh, discuss proto-bialgebroids of Reutenberg, and he does some trick to construct something which is important for physics purposes, but we prove that this construction performed by Halmagyi is actually equivalent to a construction of a triangular Lie bialgebroid. And more importantly, what Halmagyi is doing is directly generalizable to P forms. He is constructing a triangular Lie bialgebroid by using some twist method, but his method is directly applicable to P forms. So after proving that he is actually constructing a triangular Lie bialgebroid, we use the same trick for now P forms, and that works for P forms. Uh, he starts with some automorphism of the vector bundle. So this is like the identity map from the tangent bundle to tangent bundle. Here, this is a P plus 1 vector acting on P forms. So it gives a one vector field. So it gives a usual vector field. So this is a map from tangent bundle direct sum P forms to itself. Okay? So this should be read as like this. This part is acting on the tangent bundle. This part is acting on the p-forms. And by following his procedure, we define a bracket on E on the direct sum of vector fields and p-forms by twisting the Dorfman bracket. Dorfman bracket is this, just this bracket, no tilde terms or z brackets. We, by using this automorphism, we define a new bracket, and this new bracket has all the parts that we need. We can define L tilde, D tilde, and iato tilde. So this is a weird generalization of the Lie derivative. This is like a Lie derivative of a vector field with respect to a P form. So the result is again a vector field. And for example, the exterior derivative here is also weird. It eats a P minus 1 form. It gives a vector. But this is the result of this procedure. And moreover, we prove that this procedure induces the causal bracket, this bracket, on P forms. So in a sense, we extend this notion of triangularity for Lie bialgebroids to higher Courant algebroids, and instead of Poisson structures, we use Nambu-Poisson structures. And this construction is quite useful also for physical purposes. For example, if we take P is equal to 1, we get the Poisson calculus, as I told you. But this Poisson calculus business, in a similar fashion to Halmagi, is used to construct a new geometric framework called Poisson generalized geometry. This is like a analogous to generalized geometry, but everything is done by the causal bracket induced by the Poisson structure. And they have some nice results in this geometry, and they also uh, find applications in brain physics and dualities. And in this paper, we extended their Poisson generalized geometry to Nambu-Poisson exceptional generalized geometry, let's say. And we have proved some analogous results to their geometric framework in the context of now Nambu-Poisson structures. Everything, not everything works. Poisson structures are quite special in the Nambu-Poisson structure. So everything, we try to do lots of things that they have done, but some of the things they still work. They have some of them have some modifications, but still there is a similar geometric framework. More importantly, this is still an ongoing project. For P is equal to 2, we get this vector bundle. And on this vector bundle, uh, physicists already try to generalize the notion of Lie bialgebra. Since these Lie bialgebras and T dualities are quite crucial, uh, from a completely physical point of view and from physical motivations, some people defined uh, a generalization of the Lie bialgebra custom tailored for U-duality applications. And these algebras are called exceptional Drinfeld algebras. But they are not in the algebroid level. In the algebra level, which is quite important for, as I told you, U-duality, uh, are tilde calculus operators actually reproduce the non-constant fluxes of these exceptional Drinfeld algebras. At least the most basic one, SL5 exceptional Drinfeld algebra. And they have some compatibility conditions presented in the paper. We get the compatibility conditions correctly. So this Poisson structure business is actually quite useful, and uh, our framework gives us a way to express these physically motivated objects in a more rigorous way. And but there are quite important technical details for these exceptional Drinfeld algebras. So still we have lots of things to discuss, and this is still ongoing. So we we will try to understand these exceptional Drinfeld algebras in the algebroid level, uh, and this will have some applications in the U-duality framework, but this is still ongoing. And let me uh, conclude my talk with some other future topics that we will study on. We can sort of make this diagram to a cube when we integrate the algebra structures. Uh, the most simple one, when we integrate some Lie algebra, we get a Lie group. The similar relation is in between Lie bialgebra and a Poisson Lie group, and also exceptional Dirichlet algebras and some Nambu Lie groups. Uh, the integration process of the some algebraic structures is called this Coca-Chigre problem, and this is quite important from a mathematical point of view. Of course, the finding the group-like structure of a given algebraic structure, and when we elevate this problem to the algebroid level, and if we want to find a global version of these algebraids, then we arrive at bundle recoids. And in our work, we extended the formal bundle recoids of this work. They define their recoids for Kuran algebraids. We actually, by introducing another object in addition to theirs, we can extend this recoid business to higher Kuran algebroid level. So we this is a small but important extension. We extended their recoid business, which will be useful for higher Kuran algebroid. So we can sort of get the exceptional recoid if we need to give a name. We want to understand these relations and these complicated relations in a more coherent way. This is one of our future plans. And
Question? Do you mind if I ask a question just quickly?
of course,
Yeah. So just coming back to this racoid concept, you
mhm.
you you as like the lifting of a group into a bialgebroid.
Sorry, I couldn't hear the last bit.
Yeah. Is the racoid is some lifting of a group structure into a bialgebroid? Is that right?
Uh, it's not directly related to bialgebra business. If you start with some Leibniz algebra instead of a Lie algebra, you don't get a group. You get something called a rec. This
Okay.
recoid is sort of oid version of that rec. So, but this is nothing.
So,
There is nothing related to bialgebra business. Even this rec is just one Leibniz algebra, and its integration is some rec.
okay.
So not directly
And
related to bi part.
can you explain the connection maybe to the flux from there, from a racoid?
Flux and recoid.
Yeah.
Uh, I have no idea how to relate them. I don't know. the fluxes are sort of like the structure functions of the algebra, and these recoid structures are again some exponentials of algebra structures. So probably exponentials of these structure functions, so exponentials of these fluxes will appear in the recoid, but I don't know.
I see. I understand. Yep.
But
Thanks.
this is just a hunch at the moment, but the defining properties of these recoids, we hope, let me say, we didn't do the exact calculations, but it feels like it at the moment. There are some axioms that these recoids satisfy, and there are some identities called algebraic and differential identities, which are crucial for these exceptional Dirichlet algebras. And those identities sort of relate different fluxes each other. And one of the defining properties of these recoid, hopefully, we don't know, will give one of the, or will give algebraic identities. This is our hope. It feels like it, but we didn't prove it yet. So
It's interesting.
they will give some information about the fluxes, but I don't know yet the full result. Okay. Thank you for the question. So let me continue. Uh, this is like the most complicated vector bundle, at least one of them, that is physically relevant. But the bracket on this uh, vector bundle is quite complicated, and finding L tilde and D tilde for this kind of complicated bracket is also waiting for to be done. But for higher dimensional compactifications, if your compactified dimension has 7, this is the geometric framework. But this bracket does not satisfy this condition. One cannot find some metric and exterior derivative like object, a first order differential operator to express the symmetric part of this bracket. So this is a problem, and quite recently they introduced a concept called bialgebroid to study such cases when the symmetric part cannot be expressed in this form. Uh, and they introduced this notion of bialgebroids, which will also cover these cases. All of the other ones are okay, they fit into this, but the most complicated one only satisfies this. But fortunately, these bialgebroids are actually uh, introduced as some special kind of algebroids that we have previously introduced. It was a weird name, but it has a reason to. But we define something called anticommutable Leibniz algebroids, satisfying this property for some frame and coframe. And these algebroids were also quite crucial for us. For such algebroids, we extended many crucial results from the usual metric affine geometry like Bianchi identities, Schouten decomposition, Levi-Civita connection stuff. Lots of things were actually possible on these anti-commutable Leibniz algebras. This was why we were interested in, but lately we didn't see this connection, but the most complicated exceptional Dirichlet algebra vector bundle is directly has the structure of an anticommutable Leibniz algebroid. So this is a nice thing. We can actually perform quite useful identities in such algebroids. So this is nice, but we need to extend our calculus framework to accommodate these Y algebroids and anticommutable Leibniz algebroids. And lastly, as I told you, the compactification procedure makes, or the general form of these strings or branes, they have quite complicated Lagrangians or actions. But even though this is a quite complicated action, the objects are not important. There are some mathematical objects in the action, and in order to have a consistent, physically consistent theory, there should be some conditions on these objects, and these are the conditions for gauge invariance and gauge closure. And it is proven that the consistency condition for this membrane sigma model given by this are actually just frame expressions for Courant algebraic axioms. And moreover, these fluxes that I've been mentioning a few times, uh, they also satisfy some consistency conditions to be meaningful. And these conditions are also called Bianchi identities. And these Bianchi identities too correspond to the same equations. So we have a triple coincidence. Gauge closure conditions of the action, Courant algebraic axioms, and Bianchi identities for fluxes. And this triple point coincidence is also studied in this paper for the higher Courant algebraic tangent bundle plus 2 forms. This correspondence feels uh, generalizable, let me say. And since our main uh, starting point is already the analysis of algebraic axioms, we want to relate to, in the most general setting possible these sigma models, axioms, and Bianchi identities for fluxes. We want to sort of prove this triple point. If it is correct, of course, we don't know yet, but we are again hopeful, at least for some special but more general than these cases. We want to show the relation between these axioms and sigma model consistency relations, and there are lots of weird vector bundles, and for all of them this should be done. So again, we want to make it general as possible, and this is uh, one of the research routes that we want to consider in the not quite near future, but in someday. Uh, and that's it. Thank you.
Thank you, Keremcan.
Evet, sağ olun hocam.
Super.
Thank you.
So, any questions or comments?
Thanks for inviting me to the talk. I really enjoyed it.
Thank
Super
you. Thank
interesting.
you. Thank you for
Uh,
being here.
Also, season's greetings. It is Christmas Day today.
Uh, Merry Christmas.
Yeah, Merry Christmas. Uh, so, have you talked with Atabey about, uh, because he is interested in this, uh,
A, a couple of times that we discussed, but not in details, but uh, he knows, but he is like too mathematician for us, and I know some of the things seems trivial to him, but not to us. I don't know.
but it would be a good idea to discuss these things. It's related to non-commutative geometry that he's interested in.
Yeah, these fluxes are directly related to non-commutative and even non-associative geometries.
Right,
This R, there was an R twist that R actually sort of measures the non-associativity of the space-time.
right.
But that's like one sentence I can tell. I don't know the details.
Perhaps there's some connection to the monodromy hypothesis.
Connection to
So maybe some connection to monodromy. Uh,
molodromy.
simple.
Yeah.
Yeah.
Uh, uh, I don't know.
Any more questions or comments? So let's thank Keremcan once more. Uh,
Thank you.
so we will meet 2 weeks later after New Year, and Akif will be speaking this time on homotopical algebra. I don't know his title yet, but hope to see all of you. So see you all later. I'm now stopping the recording.